All right, let's examine a quick little fun problem. This is going to be a problem in R3 where I have some collection of vectors that satisfies this particular equation. So in particular, I've got a set S of the collection of things x, y, z such that 2x plus 3y minus z is equal to 0. I've got this collection of things that look like this. Okay, so what is that collection of things? Is that collection of things in particular, so is S a subspace of R3? That's the question, right? In other words, if I have two things that live on that space, can I add them up and stay in that space? If I have a thing that lives in that space and I scale it, can I stay in that space? Well, let's just understand what this space really is first. So, in particular, this XYZ, this set notation, is maybe not as helpful as it could be. So let's rewrite. What if I solve this thing for x, and I write that as minus 3y plus z all over 2, and now I've got two free variables. Right? I could really think of this as, well, actually back up for a second. I could think of it in a different way, that if I were to think of this as the end result of row reducing some system, I've got a system of equations that kind of row reduces in some sense to this. So if I row reduce one more step, that's 1 3/2 minus 1/2, 0. And zeros elsewhere, which again all comes back to that same equation. So if I were to write this as xyz equals, well, that would be minus 3/2 of y for the x's and positive 1/2 of z for the y's. Y is one of those and none of those. Z is none of those and one of those. You've seen this sort of thing before. But what we really have, pardon me, what we really have here is that this particular equation, this x equals minus 3/2 y plus 1/2 z, is the same thing as saying any point x, y, z is a linear combination of this vector and this vector. That's again equivalent to saying that x, y, z belongs to the span of negative 3/2, 1, 0 and 1/2, 0, 1. Well, okay. The span of a collection of vectors is the collection of all linear combinations of those vectors. So if I write down the definition of span here, okay, so now what I'm looking at is if I take a vector in three-dimensional space, this particular vector, and I take this vector in three-dimensional space, they are linearly independent of each other, pretty obviously. Stop and make sure that you understand why. And I can build all of the vectors coming all the way back up here that end up sitting on this geometric object, this plane in three-dimensional space. So if I come all the way back down again, this is a plane in R3. Those are two separate words. This is a plane that passes through the origin. Right? And so this thing is indeed going to be a subspace. If I take 2 points that are on this plane, so in other words, if I take two different linear combinations Let's push this forward a little bit. So if I take a linear combination of negative 3 halves, 1, 0. So this is going to be one linear combination, plus C2, 1 half, 0, 1. And add that to some other linear combination. Okay, so we'll say alpha 1, negative 3 halves, 1, 0, plus alpha 2, 1 half, 0, 1. And just add those guys up in the most naive possible way. I get C1 plus alpha 1, negative 3 halves, 1, 0, plus C2 plus alpha 2, 1 half, 0, 1. Sorry, this is a little sloppy here. This is just another linear combination of those vectors. It's just another thing in the set. So if I add two of them together, I get another one there. Pretty clearly, if I scale one of these linear combinations, I get another one there. So I know that S is a subspace of R3. If I add two of them, I get another one. If I scale one of them, I get another one of them. So hopefully this helps kind of figure out these geometric objects, these planes that you were playing with maybe in multivariable calculus or some other place. Those are actually subspaces in three-dimensional space.